Not like official, like the wrong.
We still were still 9
Hi.
What is this? I don't really I don't really go to options.
Monday, one of them is Monday, Wednesday, and one of them is I'm just saying, man. I was going to share about the
I detect a jubilant, happy mood as we get close to Thanksgiving break and maybe the end of the semester. I'm with you. On Tuesday, we arrived and went over these formulas for the sums and differences. These are, I would say the first four here are the most important. This will come up now and then. Today we're going to move forward from this. And there are going to be a lot of other formulas, and you should probably jot them down. But not as critical, not as crucial, won't come up as often. I have a few.
Did I get
You got yours back?
Yeah.
Okay. All right. Just one more. I'd like to take a pause here and discuss an issue which I'm not sure that everyone understands this very well. I'm going to make a distinction here. I'm going to write two things on the board. these are not the same thing, are they? Well, if you're an engineer or maybe a scientist or an architect student or, you know, something in the sciences, they are kind of the same. Close enough for, you know, well, you could add a few more digits. But to a mathematician, these are really different animals. This is just some decimal number that approximates a really important number, but it's not the number. And certainly since we started handing out calculators to people, the distinction has gotten a little fuzzy. To make this distinction, because we're going to use these formulas to come up with some values of the functions, the trig functions, that are exact, they're like pi. And sure, you can poke them into your calculator and get a decimal number. And if you're a scientist or an architect, a student, a computer scientist, this is fine in the end. But to a mathematician, they're not the same thing. Now, you're going to find when on the exam, there'll be at least, the final exam, there'll be at least one problem where I'll say, well, what's the sign of this? And if you poke that into your calculator, and I'm going to say exactly, if you poke it into your calculator, you're going to give me a decimal number, and I'm going to say that's not what I want. So, with that in mind, let me give you an example of what I'm looking at, what I'm talking about. What if I wanted to know what the cosine of 75 degrees was? Well, conveniently, that's the cosine of 45 degrees plus 30 degrees. Yeah. I know the trig functions exactly for 45 and 30. So using these formulas, I can determine that. So let's try. So this is going to be cosine 45 degrees, cosine 30 degrees, minus sine 45 degrees, sine 30 degrees. Now, all right, 45 degrees. Right, that's my isosceles right triangle. My hypotenuse is 1. My legs are 1 over the square root of 2. So my cosine here is 1 over the square root of 2. My sine here is 1 over the square root of 2. For 30 degrees, I have a 30, 60, 90 triangle, right triangle. Again, if my hypotenuse is 1, the shorter leg is a half, and the larger leg is square root of 3 times the shorter leg. So my cosine adjacent over the hypotenuse will be square root of 3 over 2. And my sine will be 1/2. So now I can actually tell you this is going to be square root of 3 minus 1 over 2 square root of 2. Exactly. These are irrational numbers. We can't write the decimal out, but we can have an exact value. In mathematics, sometimes we're interested in this. So, one of the things these are really useful for, just going to assume you have these written down somewhere, or you can look them up pretty easily. I think in the very, in the beginning, Stuart Calculus, they'll list them all, but our book lists them all. Similarly, we could look at this using radians. You can look at pi over 12, that's 180 over 12. That's 180 over 12. That's 15, is that right? Yeah. 15 degrees. What if we want to find the cosine of 15 degrees, or pi over 12? Well, conveniently, that's the cosine of pi over 4 minus pi over 6. So again, we have a formula for it. It's going to be cosine pi over 4, cosine pi over 6. Remember, with cosine, if it's the added formula, you get a minus, and if it's the minus formula, you get just add. Pi over 4, sine of pi over 6. And again, we can go through this exercise. Pi over 4, that's 45 degrees, so 1 to the square root of 2. 2, and again, pi over 6 is 30 degrees, so if we decide the cosine was square root of 3 over 2, 1/2, so now we get square root of 3 is 1 over 2 square root of 2 exactly. Keep this in mind. Now, keep in mind that this could be really useful if you wanted to check, right? So, square root of 3 plus 1 divided by 2 divided by square root of 2, I get 0.9659. It doesn't really matter, but it's close enough. And if I plug in, well, check my mode, of course. I'm in radian mode. So if I say cosine of pi divided by 12, well, I get the same exact number actually on the calculator. Up to 2, 4, 6, 8, 10 digits. That's good. I wouldn't be I wouldn't be surprised if like the last digit was off, because maybe it calculates a little different and there could be some round off error, but apparently not. So things you can do with these formulas. You can find exact values for some values. Now, you might say, how far can we stretch this? I mean, we've got 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees. So we can use all these in different combinations. We're going to see later today, we can find half values, 15 degrees, 22.5, we already know 30, we already know 45, and we could repeat this, 7.5, 7.25. So in principle, you could keep finding smaller and smaller increments, and you could do a lot of work, and you could get a lot of values, a whole spectrum of values exactly, but the results are going to get more and more complicated looking. You'll have square roots and square roots and square roots, so forth. But at least in principle, we can do this. All right. Any questions about this so far? Continuing along, this is part of section 7.3. We're going to learn something here. Let's just start with the formula sine x plus y. That's sine x sine y plus cosine y. Cosine x sine y. Well, there's no reason we can't, for y, make y x. In which case we've got sine x plus x, 2x, and we get what we call a double angle formula. Well, this is sine x cosine x plus cosine x sine x, just 2 sine x cosine x. Similarly, cosine of 2x is going to be cosine squared x minus sine squared x. Now, these are both really important formulas you're going to run in calculus. You go that far. This one in particular has some things we can do with it. Because by the Pythagorean theorem, we can eliminate either sine or cosine from this. Cosine of x is 1 minus sine squared of x, cosine squared minus. So I can make this 2 1 minus 2 sine squared x. Or I can substitute the other way, and I get 2 cosine squared x minus 1. Now you might say, well, if you're just trying to figure out double angle value of cosine, they're all the same. But you might have a problem where you want to eliminate one of these. You might want to just have cosine or sine in the result. We're going to get into that in a couple of days, solving equations with these, and sometimes it's convenient to just have a bunch of sine of x's in there, and we can treat it as a polynomial. You can just solve for sine of x.
No,
So, double angle, and 2x, substituting it in, you get tangent x plus tangent y, so it's 2 tan x over 1 minus tangent squared x. Okay. Now, we can take this whole idea a step further. What if we wanted the sine of 3x, triple angle formula? Well, now we have to do work, starting to get owners. But we can do this, use an algebraic system once they get more complicated. But let's just do this one, just to see how that would work. This is sine of 2x plus x. Well, that's sine of 2x cosine of 2x plus sine of x sine of 2x cosine of x.
Wait, are you supposed to do sine of 2x and then cosine of x? Instead of
Yeah, thank you.
And for the first one too, right? Because you just.
Oh. All right, let me look again. Is that what I want? Yes, that's what I want. Okay. Well, I have a formula for sine of 2x. That's 2 sine x cosine x cosine of x. And I have a formula for cosine of 2x. All right. Sine of x times cosine squared x minus sine squared x. Maybe we can do some things with this. Let's take out sine of x. And we have 2 cosine squared of x plus cosine squared of x minus sine squared of x. Is that right? That's sine of x 3 cosine squared x minus sine squared x. This might be a convenient time to put everything in terms of sine. All right? This is going to be sine of x 3 times 1 minus sine squared x. How did I do this? Pythagorean identity minus sine squared x. And what do I end up with here? Well, I end up with another mistake in my nose. That's my problem. Oh. Well, I'll take a few more steps, see if I can get it right. So that's three sine of x minus 4 sine of 4x. It's a cheery little formula. You don't have to memorize these or write these down. I just want you to be aware, we can keep doing this. We can make similar formulas for cosine of 3x, sine and cosine of 4x, and so forth. No problem doing that. I mean, you want to be able to do this algebraically. It's nothing complicated. Just realize that this is possible. Right. this though. Just want to direct this way. We can go in the other direction. How do we do that? Well, cosine of 2x is 2 cosine squared x minus 1. We could substitute here. We could replace 2x with x. Well then, over here, we'll have to substitute x with x over 2. Well, now let's solve for cosine squared x over 2. So that's cosine of x plus 1, then move the 1 over, divide by 2, write out that 2, and that's going to be cosine of x over 2. So here we have what we call a half-angle formula. It does seem a little problematic. We'll get to, we don't know if it's plus or minus. Sines and cosines can be plus or minus. We'll have to take a closer look at this when we would use each. If we start this again, instead we have cosine of 2x equal 1 minus 2 sine squared x. We can again replace 2x with x and x with 1/2 x. And solving this, we'll get that sine of x over 2 is plus or minus square root of 1 minus cosine of x over 2. And you can probably see we can combine these to get our tangent, half angle. That's going to be sine over cosine, so square root of 1 minus cosine of x over 1 plus cosine of x, plus or minus. Now, I think I'm going to derive it here. There are two other convenient forms for the tangent half angle. Tangent of x over 2 is also 1 minus cosine of x over sine of x. Or, if you prefer, sine of x over 1 plus cosine of x. To get between these, you want to recognize that, what was that term used? Well, that was a complex term. If you think about that pattern a plus b times a minus b is a squared minus b squared, well, sure enough, if you multiply 1 plus cosine of x times 1 minus cosine of x, you're going to get 1 minus cosine squared x, which is conveniently sine squared x from the Pythagorean. So you can go between these if you want. I'm not going to do that today. All right, so what can you do with this? Well, I think I mentioned we could find out the sine and cosine of 15 degrees because it's the sine of 30 degrees over 2. So, according to our formula, that should be plus or minus 1 minus cosine 30 degrees over 2, which is plus or minus 1 minus course, the sine of 15 degrees is not plus or minus this value. So here, when we're doing something like this, we have to think a little. What quadrant is 15 degrees in? First quadrant. So the sine is going to be positive. Now, if we were to take something like a good example. That would be a good example. Well, I guess what I want is 75 degrees. There are other ways to find 75 degrees. If I made a sine of 150 degrees over 2, I'd run through this same process. Oh, no, this is still in the first quadrant. It wasn't a good example. I should never do this in live, but again, the point is just sometimes when using these formulas, the half-angled sine and cosine, and you're stuck with, or the tangent, you're stuck with the and plus or minus, you may have to look, see, well, where exactly is this angle, which quadrant, and in that quadrant, what are those, what is the sign of those functions? Right. So I'm gonna draw a line here. In the curriculum, we're going to cover a few more formulas. What we've done so far are the most important ones: sum and difference, double angle, half angle. These are the ones that will come up. Now, there are some other formulas which look kind of cool, and you might think they'd be useful. They might be, but I've never seen them. So we'll kind of go over those briefly. And they're easy enough to derive, so we'll do that. Let's say we were curious about sine of x, cosine y, this product. And I guess it kind of depends on whether we know x and y. If we do know x and y, it's easy enough to multiply them. But still, we have a formula. To derive it, we're going to start with this construction: sine x plus y plus sine of x minus y. And we're going to expand these using the sum and difference rules. So sine x cosine y plus cosine x sine y, that's the first part here, and sine x cosine y minus cosine x sine y, that's the second part here. And of course this term drops. These terms are the same. So we have 2 sine x cosine y equals sine x plus y plus sine x minus y. And we can just divide by 2. So this is one of 4 combinations we'll look at. briefly. But why would we want to do that? Well, I guess I jumped ahead myself here. Let's take a look at the other formulas. So I'm gonna put them up over here. So we have sine x cosine y is sine x plus y plus sine x minus y over 2. And you can look at its reflection here, cosine x sine y, and using the same kind of strategy, we're going to get sine x plus y minus sine x minus y over 2. And we might want to know what cosine x cosine y is. Again, using that strategy, we're going to find it's equal to cosine x plus y plus cosine x minus y, and sine x sine y, which is cosine x plus y minus cosine x minus y over 2. They're all over 2. Okay, so, we have these formulas if we need them. If we ran into something like this, and we wanted this to be expressed as a product, how would we do that? Well, this is cosine of forgot, I'm going to actually have to think. Well, you want to end up with a sum like one of these, so obviously it's going to be this one. So if we want x plus y equals 7, x minus y equals 3, that's 2x equals 10, or x equals 5, and y equals 2. So we can express this as, I'm going to switch these two. Cosine of 5x plus 2x plus cosine of 5x minus 2x and now we want it over 2, so we're going to have to 2. Okay, so we apply this pattern here, and what do we get? We get 2 times cosine of 5x minus cosine of 2x. I should try doing that more often, thinking, instead of just being a parrot here. Okay, so, all right, something you can do with these formulas, convert a sum into a product. Obviously, you can go the other way, convert a product into a sum. There was something else we were going to do with this. Yeah. So, you know, you get a little practice with these in the homework. I think we're going to take a break now. Yes, questions?
How do you get to cosine 5x to cosine 2x? The last one?
How did I get to this?
Wait, how do you get to the bottom part? Yeah.
Okay, let's go over this one more time. This is what I'm starting with, right? I want it to look like this, right? So I have to find values that I can add and subtract that give me 3 and 7. So that's where I did mine. X plus y equals 7, x minus y equals 3. And I found that 5 and 2 were the values. So this is cosine 5x plus 2x, that's this. 5x minus 2x, that's 3x. And now it almost looks like this, but it needs a 2. So I divide by 2 and multiply by 2. And now what I have between here looks just like this. And this just becomes cosine 5x, cosine 2x. Did that work for you?
How is dividing by 2 and multiplying by 2 if 5 and 2 are not?
I'm sorry?
Like dividing and multiplying by 2 would just cancel out, right?
Dividing and multiplying by 2.
Would just cancel each other out.
Yeah. But I want this to have a divide by 2, because this has a divide by 2.
I think I'm just confused about how you get 5 and 2 in the end when you're like 7.
Oh, well, there's 2 questions. One is it right? And the other is how to get it. Let's just first check that it's right. Right? Cosine of 5x plus 2x is cosine of 7x.
Yeah.
Cosine of 5x minus 2x is cosine of 3x. So it is right.
Yeah, it's the second step that makes it. Like the 2 cos 5x times cos 2x.
Oh, how did I get from here to here?
Yeah.
Okay. You know, this is something, I can't speak for other subjects, but in math and in computer science, you have to make your brain into a pattern matching machine. You have to. You have to learn how to do this. So what I'm going to do to try and make it easy, I'm going to leave this up, and I'm going to rewrite this here. I'm going to use different letters, because it might make it easier. Cosine A, cosine B equals cosine A plus B plus cosine A minus B over 2. All right. Now, let's look at these two steps. Ignore the 2 for the moment. The 2 is just sitting out here. We can make believe it's not even there. Cosine A, oh, A is the 5x. Cosine B, B is the 2x. So this should be cosine A plus B. Yeah. This is cosine A minus B. This has emerged. I did not really think about this. This is a lot of math is taking something you know, taking a problem that you're trying to solve, and matching in this manner. This is very analytical. So we're just matching A for 5x. Sometimes it's not a matter of just matching. Sometimes matching something like this. Sometimes it's matching, oh, this formula is used for this. I need to do this. How do I apply it to the numbers in my problem? This is why we give you homework to practice this, because the only way you really train your mind to be able to do this kind of pattern matching is doing examples yourself. I see this all the time in Quora. Who knows Quora? They ask math questions. And they ask questions where they want you to do the problem for them. And I often don't do that. Because you have to do it to learn to do this. So, secret of success in mathematics, I guess. All right. I thought I had a kind of a number problem like this. Just check one more time, or maybe it's going to come up in the future. I guess not. Other questions? Okay, let's take a break. Again, if anyone has homework problems from the last whatever, you're welcome to pick them up on the board and look at them. If not, we'll move on. I know you two were very concerned. Are you happy now?
Yeah, I just didn't get
All
it.
right. I hope anyone else who didn't get it, stop me when we start again. I guess I'll leave this up for now. Okay, before we take a look at the next subject, I'm probably going to repeat this, probably should. We do have a final exam coming up in a few weeks. While you won't find it there yet, I will put up, kind of a study guide. The final exam is comprehensive. That means covers everything from the beginning of the class, obviously not everything, because it would take 5 hours, but everything until some point in the future that I'll demarcate. I'll say everything after this is just for fun. I will put up some practice problems. I think people appreciated that last time. I'll do that. And the rules are going to be the same. You know, you have a calculator, you can have a cheat sheet and 2 pages of notes. The exam I'm going to give you actually is going to have its own cheat sheet. I'm going to give you many of the formulas. I could give that out ahead of time. I guess I should put that out so you know what's on there, so you can know what will be available automatically. So, and I guess that's all I can say about it. It'll be a little longer than the previous exams, but not a lot. You have 2 hours for the final. So, okay. Any questions about that? Okay. All right, so the next section, for a second. The next section is on solving equations with trig functions. A lot of what you know about solving equations from polynomial equations or rational equations. Yes?
Yeah, sorry. About the exam. You said 2 pages using the front back, right?
Yeah.
Okay, cool.
Yeah. You'll use a lot of the same skills in solving polynomial or rational functions with the added challenge, fun of there might be some trig functions involved. And there is some added things that you have to be aware of with trig functions because they're periodic. Often the solution, you'll have a solution which can be restricted. If you say we want the solution between 0 and 360 degrees, there might just be one. But there might be more solutions. There might be an infinite number of solutions. And that may be what you're looking for, a general solution. So let's just start with real basic equation. Sine of theta equals 1/2. Okay. You want to solve for theta. So, theta, of course, is. Now, I'm going to try and be careful about this. And I want to say sine inverse of 1/2. Sine inverse is a function, which means it just has one result. Is that right? Yes. It just has one, because it's a function, you can only get one value out of it. But the original equation is a little different, right? Any solution that we get from this, any theta, we could always add 2 pi and subtract 2 pi because it's 2 pi periodic. But the problem is actually even worse. See, if our sine is 1/2, we have some theta. This is 1, this is 1/2. This is not the only solution here, right? Because this is in the first quarter, but in the second quarter we'll also have a solution, another angle. They're going to be supplementary angles, right? Because this angle will be theta. So this angle here is 180 minus theta. It's supplementary. So for starters, we have 2 different solutions. Anyone know what the theta is here? This is 1/2. Again, lot of cases, we can just plug this into the calculator. I guess we might as well. What does the calculator tell us? It tells me, don't misplace the calculator. I do this a lot. Let me see where I put it. No. I do this often enough. My wife has a name for it. She says that's called doing a Mitchell. And put it under something. All right, so let's let me put this into, I know the answer, but I'm going to go through this anyway. I'm going to put it in degree mode. And I'm going to ask for the inverse sign. That's, you hit the yellow button, right, the shift. And just say 0.5 as I have. Ah, it says 30 degrees. Now, why should I have known that? Because I know in a 30, 60, 90 triangle, I'm going to get these values for the sides. Okay. So, all right, let's look at the solution to this. So we know theta could be, we can just leave it 30 degrees. Now, pi over 6. It's supplement pi minus pi over 6. That's 5 pi over 6. Those are solutions to this equation. But we also want to recall that I can add 2 pi n each of these. So infinite number of solutions, they're periodic. 2 primary solutions. And it's a lot more complicated than it looked. Now, if you're just looking for the reference angle, call the reference angle is the angle in the first quadrant, well, you can just plug it into the calculator and you're done. Anything but a well-known sine or cosine, I would expect you would either do that or you would leave it, like if I said sine, say sine of theta equals 1/5. Well, that's not a well-known sign. You can say sine inverse 1/5. Okay. An exact number, the way it's written. I can't really simplify this anymore. I can use the calculator to find some decimal approximation. I encourage you in this class and in math classes in general, just leave something like this the way it is. Let's do one of these. Cosine of theta equals 0.65. So theta is the inverse cosine of 0.65. Since it has a decimal, it's perfectly okay to use the calculator. All right, we ask the calculator what this is, and we get theta equals 0.863 radians. All right, but again, we have to think, right? If we have a cosine of 0.863 here at this angle, I'm sorry. Mixing my numbers. We have a cosine of 0.65 here, and this is 0.863. The cosine is also going to be positive in the fourth quadrant. And we could write this either as 2 pi minus 0.863, or we could write it as negative 0.863. Again, you have to think about where these things are positive and negative, and where your common values of cosine and sine are. Sine is positive in 1 and 2. Cosine is positive in 1 and 4. Tangent positive in 1 and 3. Right. First and third quadrant. And of course, we're going to take these numbers 0.863 and add 2 pi n and negative 0.863 and add 2 pi n. And that gives us the complete set of solutions. So that's just dealing with very basic equations. And this is, both of these are at the level of x equals 1. Okay? That's essentially what we're doing. But these problems can be, more complex. Let's take a look at how that would work. Leave that here for now. So, 5 sine theta cosine theta plus 4 cosine theta equals 0. All right, so one of the strategies when we have a polynomial that instead of sines and cosines had x's is we do factors. You can do exactly that here. You have cosine theta times 5 sine theta plus 4 equals 0. While using the same strategy that we use when we're factoring a polynomial, we know that if a product is equal to 0, then each of these being 0 would be a solution. So we have cosine theta equals 0, or in this case, sine theta equals negative 4/5. Well, cosine theta is 0 at what? So 0 and pi. I guess we can just write this as 2 pi, no, just pi. Right? Here, and then each pi around the circle. We're going to get cosine equals 0. Here we just have the same kind of problem we just solved before. Theta is equal to inverse sine of negative 4/5. Now we have a, I think, interesting. Okay. notes have an error, which I'm glad for. So I'm just gonna wing it here. Let's do this in degrees and say inverse sine of negative 4 divided by 5. Anybody try this? You might want to see what you get. It says error syntax. Shouldn't say error syntax. It does. Oh, I did have an error syntax, not what I expected. Try again. Minus 4 divided by 5. Oh, it worked. Okay. I guess I have to think about what's the domain of, what's the domain? Well, it's from -1 to 1, so no problem. Okay. I thought I was going to get a domain error. No, I'm not going to get a domain error. I get a syntax error because I'm just going to mention this in passing. If you've ever, I think you all probably know that the minus and this minus are two different things on the calculator. The blue minus on my calculator is for subtracting two numbers, and the little minus down here is for making a number negative. Okay. All right, so no problem. It's theta is negative 53.13. And now again, I have to look at, all right, my sign is negative. Here it's in the fourth quadrant. Where else is it going to be negative? It's going to be negative here in the third quadrant. And how am I going to, this is theta, how am I going to figure out, I guess you could do it this way. How am I going to figure that out? We haven't done this before. Anyone see this secondary angle here is going to be? This is theta, right, which is a negative number. How do I get over here? Maybe. Okay, from here to here is what? It's 180. And then I'm going to add 53 to it. And I'll get this angle. So 53 plus 180 is 233.130. All right. So, you know, there I have my two angles to start with. And again, to get all solutions, you would add 2 pi n, because it's going to be periodic. All right. Well, that was a simple example of factoring. Let's look at something that's a little more devious, but not really. What if you saw this? 2 cosine squared theta minus 7 cosine theta plus 3 equals 0. So it's an awful lot like a quadratic polynomial, doesn't it? It's an awful lot like 2x squared minus 7x plus 3 equals 0. Well, that's exactly how we're going to solve this. We're going to first solve this equation. Maybe optimistic. Maybe I can inverse spoil it. Okay, so I have plus here, minus here, these will both be minus. Is there someplace I can put 3 or 1? Well, if I put 3 here, that's 6 minus 1, yay. So my solutions, x are 1/2 or 3. But I'm not looking for x, I'm looking for cosine of theta. So I get cosine of theta equals 1/2 or cosine of theta equals 3. And I'm back to solving one of the more basic equations. You can probably guess here, cosine is 1/2. Wait a minute. So that special 30, 60, 90 triangle is going to be 60 degrees plus, we're going to have to find another angle, plus we're going to add 2 pi n. What about this guy? Cosine of theta equals 3. Think about that for a second. This is where I wanted to do this on the calculator. I think. You probably can guess already if I say inverse cosine of 3. Now I get my domain error. Think about this. What does that mean? What's going on there? Might help to think about the graph of cosine. It looks like this. What's its range? Range of the cosine function? It's 1 and -1. So I can't possibly find a cosine of 3. So even though I factored this would be a solution if it were possible. It's just kind of a phantom of a solution. It doesn't add anything. Let's take a look at another one of these that isn't so nice. All right, well, optimism will fail us here, but this can only be 1. Oh, heck, let's use the rational root theorem. You remember? No, let's not. There's too many of them. What are they? Plus or minus 1, plus or minus 1/3. Plus or minus 1/9. We could try all of those. You can only have a 1 here, which is either 3 and 3 or 9 and 1. I can't get 6 out of that, right? Boiling backwards. So, all right, that doesn't work. Quadratic formula does, right? The cosine of theta equals -b plus or minus square root of b squared minus, so it becomes plus all over 18. All right. This is going to be 6 plus or minus 6 square root of 2 over 18, or 1 plus or minus square root of 2 over 3. Ah, that's what cosine of theta is. So theta is cosine inverse 1 plus or minus square root of 2 over 3. Can you already see one of these is not going to work? Have to do a little math in your head. It's 1 plus the square root of 2. Oh wait, I'm sorry. I jumped the gun. It's about 2.4 over 3. Oh no, that's going to work. Oh, never mind. 1 minus the square root of 2, about negative 4. Negative 0.1. Okay, so again, even though we can't factor it nicely with FOIL, we can use the quadratic formula here. If we, this is a perfectly exact answer. We need to do more with it, but we could use the calculator and find the decimal number. So each of these is going to produce two values of theta. So 4 values of theta, each plus 2 pi. You can see we're getting progressively more difficult here. We're going to add another complication. Well, we have a serious problem here. We don't have just an x, like cosine or sine, to solve for. We have both of these here. So the previous strategy by itself isn't going to work. But we do have an option here. We could convert this to technically it's plus or minus. So now we have an equation with just cosine theta. Well, what can we do with this? Well, if these were x's, we want to get rid of this root, so we square both sides. Let's do that. So we're going to get cosine theta plus 1 squared equals cosine squared theta plus 2 cosine theta plus 1 equals 1 minus cosine squared theta. So 2 cosine squared theta plus 2 cosine theta equals 0. We obviously can get rid of this. We get cosine theta plus 1 times cosine theta equals 0. And now we're back to, we just have to find the results. Here we have cosine theta equals -1, or cosine theta equals 0. Now, let's take a look here. So this is going to be theta is going to equal pi plus 2 pi n. And where else is cosine? Where's cosine -1? Just at 180. Right? Where is cosine 0? Pi over 2 and 3 pi over 2. Again, each of these plus 2 pi n. But we want to be careful because in getting there we did a squaring operation, which sometimes produces phantom roots. So let's take a look. So we have pi. Cosine of pi is -1, plus 1 is 0. Sine of pi is 0. So this definitely works. Pi over 2. Cosine of pi over 2 is 0, plus 1. Sine of pi over 2 is 1. So this one worked. Cosine of 3 pi over 2, that's 0 again, plus 1. What's the sine of 3 pi over 2? Wait a minute, 3 pi over 2? There's 3 pi over 2. Oh, no. I've lost my day. 3 pi over 2 is pi over 2. Pi over 2, 2 pi over 2, yeah. So, the cosine of pi over 3 pi over 2. It's -1. It's just sitting here in front of me, and it's, I guess I need fuel. If anyone's figured it out, just jump in there and embarrass me, please. Okay. Cosine of pi over 2 is 1. Oh, that's it. Nobody's watching here. This is right. What's cosine of pi over 2? It's 1. 1 plus 1. Sine of pi over 2 is... Can't do math anymore. I have to bring up the go back to woodworking. Cosine of pi over 2. That's 1. Plus 1 is 2. No.
It's pi over 2.
Cosine of pi over 2 is 0. 0 plus 1 is 1.
Yeah, so that works.
What's cosine of 3 pi over 2?
It would be 0. Cosine over 2, right?
Yeah, it's cosine of 270.
So cosine would be 0. But sine would be -1, so it would.
Yeah, okay, thank you. All right. I knew that this was...
I was like, wait, what is that?
Thank you, guys.
So that's what I meant to say, yeah.
Right. So we did have a phantom. I knew I was searching for something. Nobody helped me. Thank you. Sometimes when you square equations, you can get these phantom roots because, if I said x equals -x and I square it, I get x squared equals x squared. Well, this is correct, but clearly that's not going to work. Okay. Math is hard. All right. One last example of something you might run into. let's say you were to see something like this. 2 times sine of 3 theta minus 1 equals 0. Okay, we're good to start. 2 sine of 3 theta equals 1. Sine of 3 theta equals 1/2. 3 theta equals inverse sine of 1/2. Right, so it would be tempting to say, well, what's the sine of 1/2? It's our friend 30 degrees. So we can see right away that theta is going to equal 10 degrees. We're not quite done. See, this is really, well, let's take a look. If 3 theta is 1/2, it's also going to be, sine of 3 theta is 1/2, so this angle, 3 theta equals 30 degrees. Well, this angle is now 150 degrees. So we're going to get 3 theta equals 150 degrees. So you might think, all right, well, we've got 10 degrees and 50 degrees. Okay, good. But again, there's something missing here. We're going to graph it in just a second. Maybe we'll just graph it right now. See where we went wrong. All right. 2 sine x plus 1 equals 0. Well, probably we want to, because we have 10 degrees, which is 10 over 180 radians, and 50 degrees, 50 over 180 radians. So 1/18 and 5/18. Will you tell us what this is, Desmos? No, you won't. Well, this is probably 1/18 and this is 5/18. You can see there are other values. There's a lot of other values, although they're periodic. How do we find those? How do we find those? Well, 3 theta is going to equal 30 degrees plus 360 n. And it's also going to equal 150 degrees plus 360 n. So we have to check for a few more possibilities, right? When n is 0, we get 10 and 50 degrees. When n is 1, we get 390 over 3 is 130 degrees. We should try 2n. Right? So that would be 720 plus 30, 750 over 3, which would be 250 degrees. All right. What happens when we go to 3? So 3 times times 360, 1080 plus 30. Well, actually, we don't have to do that. We're going to divide it by 3, right? So we're really just going to get 10 degrees plus 120 degrees. And so that gives us 130, 250. The next one will be 380. 380? Wait a minute. 370. But that's the same as 10 degrees, right? Now we're just moving around. Likewise, we have 150 times 360, and so we can just divide this by 3 and get 50 degrees plus 120 again. And those are all the solutions you're going to get from this little equation here. All right, I feel like this is kind of trigonometry abuse. We're done for today. I'll be around for a couple minutes if you have questions. You'll get a little practice with this and homework. Take it seriously. Bring any questions if you have them.